In the late 1800s, Thomas Edison invented the first commercially viable light bulb. Light bulbs like this work by passing large amounts of current through a thin filament, which is basically a wire. The filament gets so hot that it starts glowing and emitting light, and this process is very inefficient. Less than 5% of the energy going into the bulb gets turned into light, and the rest gets turned into heat. A much more efficient source of light is a light-emitting diode, or LED. LEDs basically contain two specialized semiconductors that are stuck together, and when you apply a large enough voltage across them, they emit light from a process called electroluminescence. There is some heat produced, but overall the process is a lot more efficient, and you can get a lot of light from a very small device. On average, they last for over 10 years of continuous usage, so you can see why they're popular. Nowadays we have LED flashlights, LED street lamps, billboards, and even LED light bulbs. So every LED has three important things that you need to know: the polarity, the forward voltage, and the maximum current rating. Let's start with polarity, and this basically means which way do you connect an LED in your circuit. All LEDs will have two leads, an anode and a cathode. The anode and cathode are sometimes abbreviated A and C. The anode is the side that conventional current will flow into. In other words, you connect the positive side of your power source to the anode. The cathode is where conventional current will flow out from, so you'll connect your negative side of your power source to the cathode. If you get the polarity wrong in your circuit, don't worry. For low voltage projects, the backwards LED blocks current from flowing, and it just doesn't turn on. Okay, now let's talk about the forward voltage of an LED. All LEDs need a certain voltage across them in the right direction before any current can flow and they start emitting light. This particular white LED I'm using has a forward voltage of 3 volts, so we need around 3 volts before it can do anything interesting. With the supply set to 0 volts, the LED stays off. With the supply set to 1.5 volts, it's still not enough to turn the LED on. But as we get closer to 3 volts, the LED reaches full brightness. Every LED will have a forward voltage that's a little different, and here's some rough guidelines of what you can expect from different LEDs. Once the LED is on, there'll be a relatively constant voltage drop across it. Next, let's talk about the maximum current limit of LEDs. In this example, I was using a special feature of my power supply to limit the current going through the LED to a maximum of 30 milliamps, which is about as much as this LED can handle. But what happens if I take my foot off the brakes? I'm going to set the power supply to 7.5 volts, and I'm going to remove all current limits. Let's see what happens. So if you significantly exceed the LED's forward voltage rating, massive amounts of current will flow through the LED, and there's nothing to stop it from blowing itself up. Now you see why in my video on voltage, a 9-volt battery was enough to instantaneously kill an LED. There needs to be something to limit the amount of current to a safe value.
In simple terms, here's how an LED works. An LED is a basic semiconductor device. P-type semiconductor material containing positively charged carriers called holes is combined with N-type semiconductor material containing negatively charged carriers called electrons to create a diode. When a current supply is connected to the diode, the negative charged electrons are forced to move one direction, and the positive holes move in the opposite direction. When a free electron comes near a hole, it combines with the hole. The holes exist at a lower energy level than the free electron, so the electron must lose energy to combine with the hole. This energy is released in the form of a photon, or a unit of light. The amount of photon energy released determines the frequency or color of the light. The type of material and process of creating the N-type and P-type materials dictate the color of the photons, as well as the efficiency and other performance characteristics of the LED. After processing the material into an LED chip, the chip is installed in a package that allows electrical connection and directs as much light as possible in the desired direction.
So this graph here that shows the IV characteristics of various electrical components. If we look at a diode, and it could be a diode or a light emitting diode, it doesn't really matter. So let's go for an LED. What we find if there's a negative potential difference, the current it lets through is 0. And there's a certain point at which it suddenly starts to behave as a conductor. So it's basically this kind of one-way valve that only lets current flow in one direction. But the important thing is that there's a certain potential difference or a certain voltage at which it allows current to flow. And this is called the threshold voltage. So this threshold voltage is a value below which no current will flow through that diode. And this is really dependent upon the colour. And different colour LEDs have a different threshold potential difference. What I have here is a small circuit board with some LEDs on it, and it's a brilliant piece of kit for testing. So you can do this in many other sort of normal ways in the lab. And what I need to do is first of all plug it in. So I have a power source. In this case, it's just a power pack with some AA batteries. So I'm just going to put that off to one side, and you can see I've already got the red LED lit up. Now as I adjust the potential difference, we can see the different colour LEDs come on in sequence. Now the important thing is that all of these LEDs are in parallel with one another, and that means if I was to measure the potential difference across them, which I'm going to do using a multimeter, so hopefully you can just see that reading, as I just use my kind of the dial here to lower that down, what we can see is the potential difference across all of these LEDs. And as I start to increase that, we can see that the red LED comes on with a PD of about 1.5 volts. As I keep increasing the potential difference, the green one should turn on next, and we see that's a threshold voltage of about 2 volts. And then finally the blue turns on last of all at a higher threshold voltage. And what we can do is also test other LEDs here, so perhaps a purple one, perhaps an ultraviolet one, or whatever. And what we can do in all the cases is measure that threshold voltage when the light starts to shine. Here I have a rather sort of shaky diagram to show exactly the same setup. So in here we have our LED, and what we can do is we can use different values of LED. So we maybe have an infrared one, maybe we have red, orange, all the way through till we get to the sort of blue end of that spectrum. So we have different colour LEDs, and each of these has a different threshold potential difference. We've got a potential, we've got a voltmeter here to have a look at that potential difference. And actually, because it's sometimes a bit hard to tell when the LED is actually lighting up, we have an ammeter which lets us know when that current starts to flow. Here we have a potential divider circuit and some kind of source of EMF. So that's the setup that we need. And what we need to really measure are two things. First of all, we need to measure the threshold voltage, but we also need to look at the LEDs, and what we need to measure is the wavelength of light they give off. So that means we'll have a table of wavelengths and potential differences. Once we have enough results, what we can do is plot our graph with the threshold voltage on the y-axis and a value of 1 over the wavelength on the x-axis, which seems a bit weird, but it'll all become clear very soon. What we can then do is start to plot our data, and provided everything goes to plan, what you get is a graph that looks a bit like that. Once you've got the data, you can then maybe work out the gradient, and you'll find that the gradient M is equal to the change in Y value, which is your threshold voltage, divided by 1 over the wavelength, which is equal to V divided by 1 over lambda, which is just equal to V lambda. So this is what the gradient actually represents. What's that got to do with anything? How do you use that to find out Planck's constant? Well, what we know is that E is equal to HF, which is equal to HC over lambda. We can therefore say as well that the energy is equal to EV. Okay, this time E being the charge on the electron and V being the potential difference. So we can work out the energy effectively of those photons. So we can therefore say that EV is equal to HC over lambda, or we can say that V lambda, by just rearranging this, is equal to HC over E. So what I've really done here is I've had a look at the energy of each of the photons given off and looked at how that corresponds to the wavelength of that light. And by rearranging this equation, by bringing the lambda up and dividing both sides by E, the charge on the electron, we can say that V lambda is equal to HC over E. But up here, I said that V lambda is equal to the gradient of that line. So that means that the gradient M is equal to HC over E. That means if you work out the gradient, you times it by the charge on the electron, and you divide by the speed of light, you will find out the value of h, which is Planck's constant. And this should be, again, a value, I think I said it before, of 6.63 times 10 to the minus 34 joule seconds. And that's the way that you can work out Planck's constant yourself in the lab.